Plotting motion, part 2. Let's say we have a position versus time graph, which looks like this. We see on a curve here we have a changing slopes. Now we know from previous material the slope of a position versus time graph tells us about the speed. We see here slopes that are changing, which tells us changing speeds. We see positive slopes and negative slopes, which tells us we have velocities that are positive or negative. Let's imagine this curve represents the motion of a car. We'll follow that motion of a car along an x-axis, along a ruler. We see on the curve the starting position, the x-initial position, is well past zero, is greater than zero. So we have our car well past the starting position. So the car is at x-initial greater than zero. The car goes forward at increasing speed, and we see this by looking at these first three regions. The slope increases, the positive slope increases ever greater in regions 1 and 2, so our speeds are greater in 1 and 2, and it's positive, so we have a positive velocity, where velocity 2 is pointing to the right and greater than velocity 1. In this third region, we see the slope is decreasing, so our velocity is decreasing, but still positive, still going forward. In this fourth region, the slope has died away, so our speed has died away in region 4, and so it momentarily comes to a stop. In region 5, the slope is negative, therefore the velocity is negative, for the car is returning. The slope is increasing. In region 6, the car is going faster to the left, or negative in region 6. And in region 6, we have already passed the initial position, and we're still increasing towards region 7 with an increasing negative slope, which is an increasing negative velocity. Velocity 7 is greater than 6 to the left, past the initial position. Now let's say the curve dies away, a negative slope dies away, our speed dies away. So V8 is less than V7, and V9, we'll say the slope is 0, so V9 reaches a rest where the car finally stops. Now let's see the motion of our car exhibit the motion of this curve, following what we just analyzed. Car goes forward, momentarily stops region 4, reverses from region 5, 6 passes through the x-initial, all the ways back out to the origin, x position 0, where finally the car stops. So now we can interpret the motion of this graph as a physical motion. Let's say here we have another position versus time graph. On this x versus t graph, we have an increasing positive slope. What will our velocity versus time graph look like for that? Well, as we just saw, an increasing positive slope which tells us that we have an increasing positive speed. So on our v versus t graph, we have a velocity, a positive velocity that's getting ever greater. We'll say the slope increases uniformly, so our velocity increases at a steady rate. Let's say that slope now starts decreasing, so our positive slope is decreasing. So therefore our positive velocity is decreasing. This means the car, or whatever the object is slowing, but still going in the positive direction, say forward or to the right. If the slope dies away, and the slope is 0, the speed is 0. So the car or the object will be at rest. If the slope decreases, we have a negative increasing slope, then our velocity is negative and increasing. So the object, such as the car, will now be going to the left, or backwards, or in reverse, or down, or west, or south, or wherever the negative can represent by convention. So we have a car going from increasing slope to a decreasing slope, to temporarily no slope, to an increasing negative slope. So the car is going forward, slowing on its way forward, momentarily stopping, or for instant stopping, and then going reverse faster. If the slope dies away, and the speed dies away, a negative slope, a negative velocity that dies away. So you have a decreasing negative slope, which means the object is slowing. If the slope goes to 0, the speed goes to 0. So the object has a corresponding velocity of 0 at rest. What is about the acceleration versus time for this curve for this motion? Looking at our velocity versus time, we know the acceleration is the derivative of the velocity versus time. So on the velocity versus time graph, acceleration is the slopes of velocity versus time. Let's plot this acceleration, the corresponding acceleration. Positive slope on the velocity versus time, positive acceleration. Next we have a negative slope, so we'll have a negative acceleration. Even the whole slope is negative, even as it passes through zero. So one negative acceleration for the one negative slope. And then our third slope on our velocity versus time is positive. So we'll have a positive acceleration corresponding to the third positive slope on the velocity versus time. The third slope on my velocity versus time graph, this third slope here, label this 3. 3, 2, 1, 1, 1, 2, and 3. This third slope to me looks a little bit shallower than the first slope. So we'll give that acceleration a little bit less of a value, corresponding to the lesser slope on the v versus t graph. Now let's say we have this v versus t graph. We can now get familiar with the motion. Constant velocity, and let's say again region 1, and a decreasing velocity in region 2. What's the acceleration versus time graph look like? For region 1, we have a constant velocity, which is uniform motion, which means no acceleration, no slope. So no slope, acceleration is 0. Now in region 2, we have a negative slope, and we have one negative slope. So a negative acceleration corresponding to this region 2. No slope, uniform motion. Decreasing velocity, non-uniform motion in region 2. We have a positive velocity that's decreasing and a negative acceleration. We know previously that you have a velocity vector that's anti-parallel to an acceleration vector. Positive velocity, negative acceleration, anti-parallel directions, that's slowing. And our graphs are consistent with that. Let's say we have this v versus t graph, a little bit more complicated. Start out with a negative initial velocity, change our velocity, have velocity at rest, and then another change in velocity. Again, let's say region 1, 2, 3. That's it. Fix that. That's velocity at rest in region 3 and region 4. And now, initial velocity, region 1. It's a negative velocity, that just means the direction. We start out fast, a negative velocity for the first chunk of time. For region 1, we have a negative velocity, so let's say it's something going to the left fast. Then we have a change in velocity, so it's slowing. Then it reaches 0 velocity, so it's going to the left, slowing, and then by 3, the velocity is 0. And by 4, we have a velocity that's increasing in region 4, and it's speeding up. What does the acceleration versus time graph look like? Again, the derivative of velocity is acceleration. The slope of velocity versus time tells us the acceleration versus time graph. Uniform motion, acceleration is 0, slope is 0. Region 2, changing velocity, non-uniform motion. It's a positive slope, a positive acceleration. So here's our positive acceleration corresponding to region 2. Again, we have a changing velocity, another positive slope, another positive acceleration in region 4. And this will be our region 4's corresponding acceleration. Region 3, of course, had no acceleration because there's no slope. Now, what would the x versus t graph look like for this? Well, do we know anything about x initial? We know the motion, we know the change in motion from the velocity and acceleration. But do we know anywhere where this object starts its motion? We have no idea where this object starts. We cannot tell. We can only talk about the motion and the change in motion. But the origin, x initial, where it starts its motion, is totally arbitrary. We know it's going fast to the left and slowing and then stopping and speeding up. But whether it starts at the origin, passes to the origin, heads to the origin, never reaches the origin, it's entirely arbitrary what the origin is. The motion is physical. The origin is arbitrary. So let's say the object x initial is at 0. We'll assume it. Now we have one speed, negative initial velocity, uniform motion for region 1. That gives us, in region 1, one constant negative velocity for region 1, one constant negative slope for region 1. Region 2, we have a changing velocity, a changing slope. It's a decreasing slope. Sorry, it's a changing velocity. It's a decreasing velocity. So it's a decreasing slope on our position versus time graph. So we go from uniform fast motion to the left and then slowing in region 2 until we reach 0. So the position versus time graph should have one slope for region 1 and a decreasing slope for region 2. Decreasing slope, decreasing velocity, decreasing negative slope, decreasing negative velocity, which is consistent with our velocity versus time graph. In region 3, we have no slope because in region 3 we have no velocity. Region 4, we have an increasing velocity, so that means an increasing slope. And again, looking at position versus time graph, one slope, one steady negative speed, one decreasing negative slope, a decreasing negative speed. In region 3, no slope. Our object's at rest. Then the object just changes direction, it's changed its slope, and it's increasing its slope, it's going in the other direction, positive slope to the right, going faster in region 4. Let's say we have this acceleration versus time graph. What's the velocity versus time graph going to correspondingly be? Well, v initial, can we tell? No. We have acceleration versus time. We cannot tell the initial velocity. Let's say the initial velocity is greater than 0. In that case, we have a positive initial velocity and a negative acceleration, so it's slowing down again. Now let's look at this. A negative acceleration gives us one negative slope on the v versus t graph. Our negative slope, though, in the v versus t graph means starting out with initial velocity. Again, we chose to say we have an initial velocity and a negative acceleration. Again, if we have a positive initial velocity and a negative acceleration, the object is slowing. We have one negative slope on the v versus t graph, or one negative acceleration. So we go from a positive velocity, negative acceleration means it slows down, and then when the instantaneous velocity is 0, the object doesn't stop. Our object, in this case, happens to keep going, keeps that negative velocity slope. In this case, negative velocity is increasing. We have a gain in speed in the negative direction. So we have a positive velocity that's dying away. Instantaneously we have 0 speed, and then we have a negative velocity. So the object is going fast in the positive direction, slows in the positive direction, stops instantaneously, and then increases its speed in the negative direction. So from 1 to 2 to 3, we're slowing, stopping, and increasing our speed in the opposite direction. The acceleration versus time graph, we just have a 1, 2, and 3. One acceleration that decreased the speed, momentarily stopped it and changed its direction, and increased its speed in region 3 in the other direction. What will the corresponding position versus time graph look like? Let's say it's y versus t. Well, y initial, again, we cannot tell. If we do know we have a motion that's slowing, turning around, and gaining speed in the opposite direction. That's physical. Now we'll pick an arbitrary location for y initial. Let's say our origin, y initial, is at 0. So the object is slowing, which means the slope on the position versus time graph is decreasing. Positive velocity in region 1. Oops. Oh, no. Positive velocity in region 1, and the slope is positive and decreasing. On a y versus t graph, we have a positive slope that's decreasing, because on our v versus t graph, we have a positive velocity that's decreasing. Again, this is a slowing motion. Looking at that first region there, big positive slope, big positive velocity. The slope decreases till we have a region where we have no slope on y versus t, corresponding to our instantaneous velocity of 0. No slope, no speed. And that's our region 2. Now, we have a negative slope that's increasing, Because in region 3, we have a negative velocity that's increasing, so we have a negative slope on the position versus time that's increasing. And eventually we reach a steep negative slope. We have a great negative velocity at the end of region 3. So it's an object that went forward very fast, slowed down, and then reversed its direction faster and faster in the opposite direction. What kind of object can do this motion? Let's say it's a ball going up and down. The ball is tossed up and comes right back down. Let's see that again. There you go. Object goes up and down. That's what these graphs can show us. This is the graph of something that's falling motion. What is this negative acceleration that causes this one negative slope on the v versus t graph? It causes an object to go up and down, slow on its way up and speed up on its way down. Well, this acceleration is acceleration due, the constant acceleration due to gravitation in free fall.